Should be now.
All right, everybody, let's go ahead and get started. So, welcome to the Bitcoin Meetups, Chicago Bitcoin Meetups Developer Series. I just want to take time to remind everybody this is a volunteer-run organization. So we do appreciate donations. If you want to donate cash, recommend $2 to $5. Canada. If you go to our website, which is bob-chi.org, there's also a Bitcoin donation address that helps to keep the lights on. So I appreciate anybody who donates. So today I'm going to talk a bit about some pretty interesting technology. MimbleWimble, which is an alternative design for a currency network, and Liquid, which is a way of adding features to the Bitcoin network without doing any protocol changes. So with Liquid, I'm not going to get to any of the consensus stuff. I'm just going to talk about some of the features that are added, because those features are much related to the features that MimbleWimble supports. There's a disclaimer here. I am not a professional cryptologist, so this is a talk for the purposes of entertainment and not for education. As always with cryptography, you have to be super careful, and it's really easy to screw it up. And I have probably screwed up. In fact, I have most of what's written here is wrong for reasons that aren't important for a basic talk, but are if you just go and try to run a production system on them. Okay, so now that's out of the way. We're going to dive right in. So I'm going to take a little while to get started to talk about this slide here. So the whole point of doing any sort of cryptography is you want to create messages which can be read or interpreted by some, but not others. And you use these to create systems for establishing that the source of a message was a particular individual, that the procedure for constructing the message was carried out faithfully, etc. We only know a few ways to build systems like this. Almost all of them involve algebra. So this is the definition of an abelian group. Don't have to remember what an abelian group is, but the point is that we're going to be using the operator plus in situations where it may be somewhat unusual. So typically when we think about adding, we're going to be thinking about adding things like integers or real numbers, stuff that you do in like elementary school math class. But it turns out that there are plus operators which share features in common with the familiar integer real addition, but are on finite sets that are useful for actual computation. So the main things to keep in mind are there's some zero element, and if you add zero to anything, you get the thing back. Totally reasonable. If you take any element, it has a negative. So you can define for any given element A, you can define minus A. The operation doesn't care what the parenthesization is. So if you have an expression involving pluses, it can be uniquely resolved to a new value without depending on exactly how you parenthesize all the sub-expressions. And finally, the operation is symmetric. So if you have A and B, that's the same as B plus A. So you don't need to think about it in this abstract way. There are some very specific examples that show up in cryptography. One of them, which I would recommend thinking about for this talk, although it's not good to base the kinds of constructions that we're using on it, is the clock arithmetic group. So if you've never seen this before, there's this really simple observation that you can make where if you have the 12 numbers on a clock face, they form an arithmetic under addition. So if you add a certain number of hours, you get a well-defined time throughout the day. So you have these 12 values, and if you were to add 13 to 1 o'clock, you get 2 o'clock. So 13 hours after 1 o'clock is 2 o'clock. So it wraps back around. And you can do this for any number, actually. So if you do this with the numbers 0 and 1, this is the algebra of evenness and oddness. So if you think about it, adding two even numbers gives you an even number, and even and an odd gives you an odd, and two odds gives you an even. So that's the arithmetic there, and it's the same arithmetic, actually. Your question?
Yeah, just kind of the question in observation. Would this also be kind of similar to XOR logic if you're dealing with permanent?
Well, the evens and odds example is XOR. So if you think of these as bits, I've just described the XOR operation.
Okay.
Yeah, exactly. So that's a great example, and typically what will happen is you'll take a prime number of elements, and the reason for this is because if you have a prime number of elements, then you actually get some additional operations. That's not going to be important for the level of the talk that we're going to be doing. The other one is elliptic curve groups. So we could have spent the rest of the time scratching the surface of what an elliptic curve group is, but suffice to say that it's a group that you can calculate with, which supports certain efficient operations, and certain operations are not efficient in this group. And that's the really important part. So whenever you see an elliptic curve group, you really should not think too much. So if you're like a casual reader, or if you're observing a conversation or you're looking at a paper and you see somebody talking about an elliptic curve group, I think it's fine at a first blush just to imagine it as being an analog of one of these clock arithmetic groups. Mainly, there are finitely many possible values, and it supports a plus operation, which behaves like the plus operation in the integers. So whenever you have a plus operation, you can do it some number of times, and now you get multiplication by integers. So whenever you have a number, and you write that times a group element, what you're doing is a shorthand. Actually, if it's an integer, if it's a natural number, it really is. So it's a positive integer. It really is shorthand for you have a positive integer that corresponds to the number of terms in a sum. Set all those sums equal to that element. That sum value just added it to itself over and over again. That's now what we're calling n times that value. And if n is negative, well, you just do n times the negative of that value. So there's always a negative. What happens if you take 0 times some group element?
You get 0.
You get 0. So that's a convention. So we're just going to define. So of course, what is 0? What is a sum with 0 terms? Well, we have to define it. It's 0. Yeah. So getting into some of the way that we think about security, there's basically two broad approaches to thinking about the security of computer systems. So one of them has to do with whether or not some sort of threat is actually possible to carry out. So you might have a system where you show through some means that something that you're worried about is actually impossible. It's mathematically impossible. So you can prove that it's impossible. So this is typically kind of alive, but this is typically what's considered to be like information theoretic security. So, or mathematical security. The other kind of security, when you're thinking about analyzing computer systems, is you have a threat, but that threat doesn't have unlimited resources. So there may be attacks that could be carried out in principle, but they might require more energy than we've observed in the observable universe. So such a threat, while it may exist, and we can discuss it and we have some formal properties, it's not a serious threat. So any threat that requires more resources than your attacker can muster is not a real threat. And so we typically characterize these in terms of the probability that an attacker can attack you, given the size of some problem. So when you have this information theoretic security, you typically don't have any parameters. So someone will say, this is secure in a non-parametric model. Whereas if you have this more practical approach to security, now you have to start saying, well, it's secure. Its security depends on the size of some parameter. So there's some parameter, and you have a construction that you're doing. So you have a systems design, and you have an instance of the system for all values of that parameter, and the guarantee is that you can exhaust the resources of your attacker by making that parameter large. And ideally, when you make the parameter large, you don't exhaust the resources of the people who are trying to use the system for what it's designed for. So you exhaust the attacker without exhausting the participants. Any questions about this? Yeah.
I just wanted to know, earlier you mentioned that for the clock system that you use the prime numbers, would also the Carmichael numbers also have the similar properties, or?
So this is just, it's a very simple thing. Is you just take, so you're going to fix a size, right? So you want to find a very simple arithmetic with a given number of elements. So what you do is you take the first n integers, so 0, 1, 2, 3, 4, whatever, up through n minus 1. And now if you want to add them together, well, because they're just integers, you already have the sum defined, right? But the problem is that when you add two integers that are less than or equal to n minus 1 together, two non-negative integers, then the sum might be more than n minus 1. What you do is you take that and you can divide that by n, and you get a remainder. And that remainder is defined to be the result of the addition. And it turns out that that has those properties. So a really nice way to think about this is your arithmetic is the symmetries of an n-sided polygon. So there is the rotational symmetries of an n-sided polygon. So you have an n-sided polygon, and the number 1, in this case, corresponds to a rotation by 1 step. And so now what happens if you rotate by, 12 steps and then 15 steps, right? So you have a 27 rotation, and if your polygon was only 20-sided, what is a 27-step rotation of a 20-sided polygon? Well, that's the same as a 7-step rotation. If you're only caring about like the labeling of if it's divided into colored segments, you have 20 colors, and all you care about is like the visual appearance, then that 27-fold rotation is really just the same as a 7-fold rotation. So that's another, if you're more of a geometry person, that's a way to think about this arithmetic. That addition is addition of angles, essentially. Other questions? Okay, so when you're doing cryptography, one of the things that you want to be able to rely on, if you're trying to exhaust the resources of your attacker, is you need some problems that are hard to solve. So some problems are impossible, and some problems are just hard. This list is a list of problems which have a parameter, which if you make the parameter large, you can make the resources required to solve the problem large. So these are discrete logarithm, prime factorization, and hash inversion. So I'll get to hash inversion in a little bit. Prime factorization is just you have a number and you want to find all of its prime factors. The one that's going to be most important for us is this discrete logarithm problem. So this is the problem of if you have a number that can be written as n times a, but you only know that number, and you know a, what is n? So can you find a number such that multiplying one of the group elements gives you another one? So this probably doesn't make a whole lot of sense as a problem when you're thinking about XORing bits or rotating polygons. And it isn't. The discrete logarithm problem is very easy in these groups. But the elliptic curve group happens to be a group where even though you can efficiently add points together, you can't efficiently find the multiplier where one point is a multiple of the other. And so the idea of a lot of protocols is you have a problem that is assumed to be hard. So, okay, I should say these hard problems are hard because we don't know of efficient ways to solve them, not because there is an ironclad proof. So in fact, you can, the actual difficulty of discrete logarithm or prime factorization in general is unknown. I mean, this is related to a very difficult open problem in computer science. But in practice, we have very important systems which use these problems as the basis for their security and have remained impervious to attack over the years. And so we tend to assume that these are actually hard problems. And so if you have some system that you're analyzing and you want to understand whether there are any formal attacks on the system. So we're not going to consider like a social engineering attack where you just trick somebody into giving you a secret. Just by correct operating of the system, can you somehow break the secret, forge a signature, break the encryption? So in order to argue that if you're just allowed to use the system as intended, you can't actually break it, typically that's a reduction. So you make a bunch of arguments, and at the end of the day, you said, well, if you can break that system, you can break discrete log. And we don't think people can break discrete log, so it's secure. So that's kind of the pattern when people are analyzing the security of systems. I should say, so discrete logarithm is a problem which is tractable on quantum computers. So this is why, if you've heard people wringing their hands over the state of affairs of commercial cryptography, it's because all the commercial cryptography that we've deployed it just crumbles under the onslaught of a powerful enough quantum computer. And then you could discuss how likely it is for such a thing to emerge soon. Okay, so another important idea in security analysis is a random oracle. So I should probably like give you some landmarks. Like why are we talking about this instead of talking about MimbleWimble? Well, the main reason we're talking about this instead of talking about MimbleWimble is because I think it's useful as a warm-up. So we're going to be doing a bunch of just like nitty-gritty messing around with algebra and understanding how you can compose a cryptocurrency protocol. But you might be curious about like how do you actually start to approach the question of like, is this protocol sound if people are using it correctly? And these are the sorts of ideas that people use to write arguments. And these arguments have, they have the benefit of clarifying your thinking about what it is you're actually doing, but they also have the drawback of being largely irrelevant to the actual security of the system. So typically there's a different, so the arguments are made and the proofs are carried through under certain assumptions, and then if any of those assumptions is wrong, then it's just the whole thing is out. So for random oracle, wouldn't it be nice if we could take two sets that we care about, like maybe one of the sets is strings of length up to 1,000, and the other one is strings of length 20. And wouldn't it be nice if we could just sample uniformly at random a function from that space? So there's finitely many ways to write down for every single string of length 1,000 a corresponding string of length 20. So we can consider them all equally likely, just grab one at random, and use that to do cryptography. And I'll show you where this idea gets applied in some later slide. Well, that would be a useful tool to have, but it's impossible to actually do this. And the reason is because if you take a random function, there are pretty strong theoretical results that say that you can't actually represent it in space less than simply writing down its table of mappings. So if you have a large domain, like you have some space of strings of length 1,000, and you're writing down a 20-bit string for each of those. Now that's a very large that's a very large set, and the data that represents that function can't be written in any more clever way. However, so when we're dealing with the security analysis of computer system, one of the things that you'll often see is this random oracle hypothesis. And this is saying, you know what, it doesn't matter that you can't actually use these functions in practice. Let's just use them in a theoretical way. So you have some information channel to the netherworld, and you have some daemon there that's going to compute for you the values of a random function. And it's going to cost you a single instruction. So that's the assumption. Okay, so now let's actually look at a protocol and try to understand what's going on using some of these ideas. So this is the Schnorr identification protocol. So the assumptions that we're going to make are that we have a group, which we'll call A. So maybe the clock group, although not really, because it doesn't have the part discrete logarithm problem. So typically this is an elliptic curve group or an RSA group, and we have a specific element of this group, so it's non-zero. So like in the clock setting, what we've got is we've got a clock group and we've got the number 51. So we have a very specific collection, a very specific data. And now the point here is that because of the discrete logarithm problem, if you just pick a random number, and you multiply that group element by that number, the resulting value, it's again a group element, but because of the discrete logarithm problem, you can safely publish that number without revealing the secret value you used to compute it. So this is the basis of asymmetric cryptography. So you have a number that you can produce a shadow or a transformation, which produces a public value that's one-to-one corresponds to that number, from which no one with the bounded resources that they have can compute that original value. Okay, so we're going to use this to we're going to have our two participants, Alice and Bob, and Alice is going to prove to Bob that she knows the special value. So she knows that x such that p is x times g. So how does this work? Well, first of all, Bob is going to just choose a random number, and Bob is going to send that number to Alice. Now, what Alice does is Alice will choose a second random number, and she will construct two values. So she'll take Bob's number, multiply it by her secret number, and add her random number. Both of these, the C value and the R value, are called nonces, or numbers used once. So Alice has a nonce, Bob has a nonce. Alice does a little bit of multiplication and addition. And Alice also provides Bob with this number, her nonce times the special group element. And then Bob just checks that checks an equation. Okay, so regardless of how addition and thus multiplication are actually defined, these are simple arithmetic equations that can be implemented very efficiently on a computer. Now, let's look to see whether or not someone can fraudulently represent themselves to Bob as Alice. What would it actually take in order to represent yourself as Alice? So the point is that if we have an attacker named Mallory, the way that if she doesn't actually know what that x value is, the only way that she can, her likelihood of convincing Bob that she is Alice is about the same as her likelihood of solving the discrete logarithm problem, which is negligible. And so because a solution to breaking the Schnorr protocol can be converted over into a solution to breaking the discrete logarithm problem, we consider it to be secure because we consider the discrete logarithm problem to be this like bedrock on which our crypto systems are founded. So in some details, I'm sorry this is a little bit small. So let's suppose that you could have an algorithm that if you're given a public key and a nonce, it'll output a signature that passes, or passes with probability p. I mean, just imagine that it passes. then all you have to do is you can solve for the public key, or the private key. So if you have a signature that passes, then you can solve for the key value, and now you've just broken discrete logarithm. Because you can run this on any P in any nonce, so any public key. So if you can break not just Alice's public key, because like maybe with Alice, she's her birthday as her private key or something, just guess it. But like in general, if you could break all instances of this efficiently, then you can break discrete log. Are there any questions about this calculation? Yeah.
Would there actually be, would there be an actual limit? So if we choose like a very small group, that that you can't easily guess the.
Yeah. So this probability thing, right? So like one of the things that we could do with our algorithm break is let's just guess randomly. Just like randomly sample two values S and R. So for very small groups, that output, right, just a random guess has a decent shot at breaking the signature. So both of these values S and R are numbers, but like because the way our group works, it only matters what they are upon division by the size of this group. And so let's suppose that you had a group of size 10, right? So now, how many ways are there to choose two values between 0 and 9 inclusive? Right? There are 100 ways to do that. So to produce a correct signature, you have a 1 in 100 shot at doing that, just by random chance. And so you need the group to be large in order to make it so that your random guessing strategy has reasonable tolerances. So you want to make it very unlikely that random guessing will break the protocol. And like 1 out of 100, like that is not very good, right? Because like in fact, with a small group like that, if you have access to Bob and Bob will answer multiple requests, like Bob's a server somewhere, like you could just try all possibilities until you get in, right? So the size of the group is very important. Other questions? Yeah.
How would you determine if someone's open sourcing a wallet or a framework to know which path they went? Because something I'm thinking about is like, okay, everyone puts out their code to GitHub, and I'm looking at the white paper, and I'm looking at their wallet, and I'm trying to figure out how to hack either the wallet or framework, then that's kind of horrible.
Well, this is a very practical question. So the question is, how do you break computer systems? Right? You have access to the code. You don't need to do any reversing. I mean, there are a lot of very specific ways that people implement these things incorrectly. You can spend your time becoming an expert on those ways and capturing, I don't know, what it's probably the 80-20 rule here, capturing 80% of all errors, right? So like people who implement cryptography wrong, my guess being somebody who is likely to implement cryptography wrong, would be that they implement cryptography wrong in very specific and sort of boneheaded ways. People who are working on very complex, or who are experts, are likely to get a lot of the basics right, and the mistakes that they make are more likely to require like very careful study, and they're likely to be idiosyncratic. So if you're analyzing like a wallet implementation or some piece of crypto in some piece of software, your best bet is to, and again, this is just my like fairly amateur opinion, is to learn about the top like 20 ways that people misimplement cryptography, try them all, and then move on to the next one. So you have to use your resources wisely, I guess. Other questions? Okay, so now we've got this scheme by which Alice can identify herself, Bob, and the last ingredient here is now we want Alice to be able to create such a proof of per identity without requiring Bob's input. So there's this thing called the Fiat-Shamir heuristic, where instead of Bob providing a challenge, what we do instead is we have Alice provide a random function input. And the way that this will work is, so we have a random function, h, and what we do is we just feed in, Alice computes her public nonce here by taking her private nonce and multiplying it by her special group element. And then she just takes the random function and applies it to that. And why is this okay? Well, the reason why this is okay is because an attacker wouldn't be able to predict. So basically, given given the public nonce value, this value is essentially randomly distributed. And so this still satisfies so Alice can't, Alice has essentially no power to like select a good H value that for nefarious purposes, if the function is truly like random. Yeah.
Yeah, I just was wondering, you said that it was randomly, is it randomly uniform or randomly
you can mean lots of different things. I mean, I think typically you have a function space, so all the possible functions with the signature that your function has, and just pick one at random. That's what a random function is.
So basically it is uniform. During each iteration, the possibility of each using the same random function is all.
Well, so the random function is like input to the scheme, to the signature, or to the protocol. So you have a random function once and for all that's used for all rounds of the protocol.
It's a particular function.
It's a particular function with random values. So like for example, if there were to be two people who chose the same R value, then the H of R would be the same. And of course, you want the probability that two people choose the same R value to be very low. All right, yeah. So now, just how do we convert this into a digital signature scheme? Well, we have to add a message into the mix, and this is actually quite simple. We just consider instead of taking a function that takes group elements to a scalar value, so where a scalar value is a number between, yeah.
Quick question. What's, in this context, what's the colon equal? Like, what's that syntax?
Oh, so my syntax here is just saying that we're defining something. So we have an S value here. We're not trying to test equality or anything. Equality is two equal signs. This is just saying that there's this point that we're going to compute, and this is its definition.
So it's basically just the same as the sign.
Yeah, but I'm just trying to make it like visually clear that we're not like S doesn't already exist. Like this is what S is.
Okay, so it's an initialization of sign.
I mean, it's like that's an implementation detail of your language. I mean, this is just really conceptually. We want to call this like complicated expression S in our signature protocol. Okay, so now I'm going to go through some discussion of committing. So we talked about how do you identify, how do you sign, and how do you analyze the security. Just super high level. I'm going through a little bit of stuff about that. Now, how do you commit to a value? So the point here is we want to be able to establish that we're working with a certain value without necessarily revealing what that value is. So according to the discrete logarithm problem, we actually have done that. So with the discrete logarithm problem, if we have a totally random value, we can just multiply it by our group element, and now we can publish that, and now there's a one-to-one correspondence between values and group elements, so we're golden. This works very well unless you are in a situation where you want to commit to a value which is in a small set. So if you're really choosing a random value, just multiplying it by the group element will perfectly well commit to it, going to figure out what it is. But if you're trying to commit to a value between 1 and 100, right, someone can just test all of the values 1 to 100 and figure out which one is your value. so it doesn't hide anything. So in this case, let's just make this a little bit more formal. So we have two components to our committing scheme. The first component is an algorithm which creates the commitment, and the second is an algorithm which opens the commitment, mainly meaning that you have some existing commitment, and this can prove that it was associated to a particular value. So the properties that we want to have are the binding property, which means that it's impossible to change it's impossible to lie about which value you committed to later. So specifically, there shouldn't be two values. Oh, I changed this a little bit. So let me just explain. The commit algorithm here takes two parameters. You can just ignore that for now. I'll say why that is later. But the point is just a property of a good commitment scheme is it actually has to be the case that it forces you to have been talking about one value. Like it can't be ambiguous. So the failure of the binding property to hold is ambiguity in the commitments. You want unambiguous commitment schemes. The other property that you would want to hold is this hiding property, which just means that you can't crack the commitment open and see what value is inside. So a person with bounded resources, they can't just scan through some small space and figure out what value you get. Okay, so here's a particular example of a commitment scheme which has those properties and which will work even if your value is in some really small set. So you can commit to a value between 0 and 1, as well as you can commit to a value between 0 and 256. So in this case, the trick is that we include a little bit of an extra random value in there. So we have the value that we want to commit to, but we also have a random blinding factor. And we start out by choosing 2 points where their relative discrete logarithm is not known. This is kind of complicated. I don't get into how you actually wind up with those 2 points. But let's say that we have those points. Nobody knows their relationship in terms of the arithmetic. To commit a value, we first sample an arbitrary value, just uniformly at random, and then we take a combination of points. So here, for people who can't see it very well, so we're multiplying one of our group elements by the value that we want to commit to, and then we're adding to that a multiple of the other group element by our random factor. So we give our commitments are structured. They're always something committed value times G, first generator, plus random value times H. And in order to open them, well, we just reveal both the value that we committed to and the random value, and you can check just does the commitment have that form. And this is both binding and hiding. So if you have a hard discrete logarithm problem for your group, then your adversary can't, or like users of the commitment scheme that are dishonest, can't lie about what value they committed to in the first place, and they can't figure out what value was committed to before the commitment is opened. It has an additional property, which, since we're doing algebra, wouldn't it be nice if there was algebraic structure here? The additional property is that committing in this way actually has a nice compatibility with the addition property. So if you have 2 commitments and you add them, you're committing to the sum. The sum of the commitments is the commitment to the sum. And the randomness is related as just the sum of the 2 randomnesses. Okay, so now let's get into the actual interesting cryptocurrency stuff. But before I get started on this, does anybody have any questions? Is everyone feeling warmed up now? Okay. Yeah. That's my one motivational speaking. Okay, so here we have this problem where you're on the Bitcoin blockchain and you're a transaction and you feel naked because you have listed exactly what your inputs are and their amounts, and exactly what your outputs are and their amounts. And we want to find a way to make sure that people can't see what those amounts are. But we don't want to give up the nice property that the verifiability property that Bitcoin has. We still want to be able to show that a transaction didn't just create new Bitcoins or destroy them, which is the same. So, well, actually, the transaction can destroy them. We really only care about creating them. Okay, so for a confidential transaction, and there's a hard part of this that I'm just going to completely ignore because it's a bit more technical than everything else. But instead of having just simple amounts as inputs, we actually have commitments to amounts, these Peterson commitments to amounts. So now, instead of just having an amount as an input, if you are the owner of that output, so remember every input is spending a spent output. So from the point of view of just a random observer, that output just looks like a random, in this case, it looks like a point. But if you are the owner of that output, or if you have the information that's needed to spend it, it looks like an amount together with a blinding factor. So it's actually a pair. So all of our inputs have the structure of being, privately a pair of values, an amount and a nonce, and publicly just a point. In the confidential transaction setting, we have the signatures as well. So we have outputs are associated with a key or a script, and we have to give the signature if we're going to spend it. Similarly, outputs are also commitments to outputs. So given an output from the point of view of just a random blockchain observer, again, it's just a random value, it looks like a random point. But to somebody who created that output, it's an amount and a blinding factor. Now, there's a detail here which is very important, but I'm not going to really discuss it all, which is that if you have a commitment to a small value, you have no way of knowing without seeing that value that it was a small positive number. And so in addition to these commitments, you also need some proof that the amount committed to was actually between 0 and some upper bound. And that's a very interesting topic, and I'm just not going to discuss it at all. Okay, so notice that, and there's also a fee. So notice that there's an equation that's satisfied if the transaction is balanced. So the sum of the inputs plus the fee has to equal the sum of the outputs. This is just accounting 101. And if in addition, the sum of the commitments behaves in this way, then when you the sum of the nonces balances, then the sum of the commitments, so if you add the outputs and subtract the inputs, the result will be the fee times a known point. And so this is the balancing equation for a confidential transaction. So you have a bunch of input commitments, and you have a bunch of output commitments, and you have a fee, and the sum of the output commitments minus the sum of the input commitments has to be equal to the fee times a specific point. And because of the properties of the commitment scheme, if you don't know those values, you're not going to be able to balance the transaction. Okay. We can, in this case, what we're interested in is checking to see that the transaction doesn't create new Bitcoins. So if we have range proofs, then this is enough. This equation, the equality here is enough because nobody knows how to write G as some multiple of H. So if this transaction didn't balance, you would wind up with a value that looked like some random UG plus VH. And now you're obligated to write that as a multiple of G, and you can't do it. You just cannot do it. Question?
Yeah, I was just wondering, you said that we don't care about Bitcoin or whatever cryptocurrency is being destroyed. However, if our cryptocurrency is destroyed, would that also unbalance the UG plus H?
Yeah, I was just, you just throw away that comment. It's not important for understanding this. Yeah, so I mean, the point is, like, we want the, whatever you list as the fee, we want this to hold. Like, we want accounting at the transaction level to be checkable, right? Like, accounting at the transaction level can only mean one thing. And like in Bitcoin, like, the only thing you can ever do is pay the miners, and like, you might, right? Like, if the inputs and outputs don't balance properly, that's just the fee, right? So anyway, yeah, that's a kind of a non sequitur. Okay, so now we're ready to talk about MimbleWimble. But before we talk about MimbleWimble, are there any questions about what we're doing with confidential transactions, what confidential transactions achieve, how they achieve it? Yeah.
Is this only going to proof of work and is solar or proof of stake?
So I haven't talked about the consensus mechanism at all. All we're doing is we're checking transaction level accounting here. So we're hiding the values of inputs and outputs at the transaction level. And you can use this to structure your ledger. So you use this to structure your ledger, and then you can get consensus over what the global ledger state is using whatever your favorite algorithm.
Because I was trying to figure out why you would bring that hiding a few seconds ago.
Okay, non sequitur, like that somehow, like I said something about destroying Bitcoin, and it like turned into a whole thing, and it's not
okay.
at all. Yeah. So there's no need to think about mining. There's no need to think about consensus here. This is purely just like how do you implement a currency? How do you implement a transaction ledger in a way that doesn't reveal the amounts? Okay, so that brings us to MimbleWimble, where we're going to actually use this idea of confidential transactions, and we're going to bootstrap from this a very interesting way to structure a transaction ledger, which will allow us ultimately to erase the transactions essentially completely. So with MimbleWimble, instead of so we have this transaction which in the case of confidential transactions, the transaction needed to balance. But what if we added? What if instead of this we have what if we rewrite this as an equation? Inputs plus fee times our curve point equals sum of the output commitments. Right? Now it balances exactly. And what MimbleWimble notices is that this is allowed to not balance as long as it doesn't balance in such a way that you know how to write the defect. So if you can prove you know how to write the failure of that to balance, you can use that to prove ownership of coins. It's a very beautiful idea.
Wait, can you say that one more time?
Yeah, so what we're going to notice is you have this accounting equation, right? And I was writing it in one form that has some of the input commitments, some of the output commitments minus the sum of the input commitments equals a certain kind of commitment to the fee. So we can move the fee to the other side. Now it's equal to 0. And with MimbleWimble, instead we allow it not to equal 0. And as long as someone can, in its most general setting, as long as someone can open that commitment, then they can prove that they have secret information that authorizes them to sign that transaction.
Okay.
We're actually going to do something slightly different than that. But basically, what it is we're going to allow the transaction not to balance, and we're going to leverage that to get ledger integrity.
Gotcha.
Okay, so now Mimble transactions are oh, I think I lost the slide somewhere. But anyway, MimbleWimble transactions are constructed interactively, and you'll see in a minute where this non-balancing comes in. So first of all, let's say that you have a payer, and the payer owns some outputs according to the system. There's sort of a recursive. This definition is a little bit recursive. It's like I'll tell you at the end what it meant at the beginning to own stuff. So the payer collects a bunch of unspent outputs, and again, these outputs are pairs of an amount and a blinding factor. Because they're amount and a blinding factor, you need proof that they're not some negative number or something like this. We omit that proof because it's hard to explain and hard to understand. Then the payer defines a change output and a fee. Okay, so now we're going to spend some outputs, but so these will become the inputs. So we're going to spend some outputs, we're going to create a new output paying ourselves change. We decide on a fee. Then you take all of those secret values. So you've got your secret commitment values that only you know, and you form this special value, which is the sum of the unspent output, which are transaction input commitment nonces, minus the nonce of the transaction of the change output, and we're going to send that value to the payee. So whoever we're going to pay, we're giving them this value. At this point, as soon as the payer learns what the outputs are, they may not even need that much. As soon as they learn this value, they effectively own the coins. So they have enough information to create a transaction that spends the coins to outputs that they control. So now they define new outputs. So you're receiving this MimbleWimble coin, and typically you'll probably have like one output, maybe two. But anyway, you define as many outputs as you want. They consist of an amount and a nonce. Then you construct the nonces in such a way that the nonces satisfy this balancing equation. Oops, there should have. So this fee shouldn't be there. Oh yeah, no, the amount. Okay, so here we've got an amount balancing equation. That is correct. Then we have from all this information, so we have the input commitments, the input nonces, from which we can recover the input values if we want. We'll probably just get them in some format. A change output, the difference of the nonces, the sum of the nonces from the inputs and the change output, and then we have the sum of the output nonces, and this difference here is a secret value that only the recipient of the coins knows. And I probably should have had the equation on here, but if you imagine what happens if you sum the commitments, so you have sum of the input commitments, so you have the sum of the output commitments plus the sum of the change commitment minus the sum of the input commitments, minus the fee commitment. Now that's going to be equal to a public key. So that's going to be equal to this secret value times a specific one of those 2 points. So in the notation that I use, it's going to be k times h, and we can use any signature scheme we want to sign that. So we may as well schnorr sign it. And we create a generic signature, so it might be, we sign an empty message or something like this. But we just have to prove that we know that value. So we have a public equation, the balancing equation, which gives a public key, and we have a private key, and we can sign for that public key now. And so what we're doing is we're proving that we know that equation. We know the value. Okay, so I think there's some stuff that's going unsaid here, unfortunately, and it's not on the screen. But the point is that we're trying to leverage the fact that the nonces for all of these commitments are private information. And the idea is that someone can spend an output, like the model of ownership that we're using is someone can spend a set of outputs as soon as they know the sum of their nonces. So like the condition for owning outputs is a collection of outputs. You can even own them jointly without owning them individually, which is a weird thing about this. So the condition for owning a set of outputs in the system is the sum of their nonces. So you compare this to something like Bitcoin, where the condition to owning an output is you need to be able to produce a script that redeems. You need to be able to, let's just keep it simple. You need to know how to sign for the key associated with that output. So you're revealing a secret. Here, you don't have a key attached directly. You have a key attached implicitly via these nonces. So what we're doing is we're actually viewing the nonces as secret keys. So now the output commitment is a combination of an amount and a secret key.
So this is, this might be a little bit of more advanced question, but so if somebody previously owned a coin and then we spent that coin, then the person who owns the coin would also have would have like.
So there's a double spend problem. So the double spend problem is solved by your consensus system. So this is not that useful if you're not embedding all of this information in, some ledger somewhere that everyone agrees on. So yes, so if multiple people know a secret, then that creates, and the secret is required to spend some coins, then that creates a double spend problem, and we solve this using a blockchain. Typically. So proof of work, proof of stake, however you like it.
Okay,
Do you have a question?
For the same notion, if I have like 5 transactions, say that I look at content, how do let's say that I spend 1, 3, and 5 of them, then I spend 2, 3, and 4. How does the network know if the amounts are all pretty reconciled? If I spent partial amounts of each of those various components, how does that get?
So you have to mention the output that you're spending.
Right. But
so you don't know.
right?
So like it's going to be public information, which outputs are spent, but it's not public information what they're amounts. So I'll get to that actually later. I'll talk about block structure. So like how do you, because like you can actually use this to, so like this ultimate, well here, let's just get into it. Yes.
Between something being on chain and a side chain and being on the primary chain, could those be a way of people kind of looking at each other? I'm trying to think of this idea that if something's on the side chain, could that be the secret from what would be on the main chain?
Well, it depends on what you mean by on the side chain, because like typically the side chain is public information. So there's some public state and then there's some private state that individuals know. So of course nothing that's public state can possibly be secret because everyone knows.
True.
Yeah. Now we may have some enforcement of mechanisms whereby something happens on the side chain and then everyone agrees that it should have side effects on the main chain. Like, that's something that you could try to achieve, but that's not revealing secrets. That's, additional rules around what's valid. Okay, so so this is a really cool property of the MimbleWimble system, which is that in some sense, like we don't actually care how the transactions are organized into transactions. Like the balancing equation can, all of the balancing equations can be combined into an arbitrarily big balancing equation without worrying about the whether or not individual balancing equations balanced. The structure of a block, at least at a very high level, is, so there's a block header with some information about that's relevant for consensus. But in terms of like how it's organized in terms of transactions, we have a list of inputs that are included in the block, a list of outputs. We have a total fee. I don't know why this is like creeping to the right. And we have all of this defect. So remember that like you had a transaction and you wound up with a secret key, and the public key for that secret key was the result, was the failure of the transaction to actually balance. So that defect needs to be recorded. So every time there's a transaction, you create a defect. Those defects live forever in the blocks. Now, you can check that a block is valid simply by making sure that the defect signatures are valid. So for every defect that was introduced, was the transaction recipient able to actually construct a signature? So they have to prove to you that they know how to write that defect as a multiple of some elliptic curve point. They can't fake balancing the equation, because if they fake balancing the equation and just put arbitrary values in, they wouldn't be able to sign the resulting thing. So we have the wrong structure. Remember, you don't know how to write, so you have these two elliptic curve points, G and H. One of them gets the nonce, one of them gets the value. You can't write G in terms of H, and you can't write H in terms of G. So if you have to sign something to prove that you know how to write it as a multiple of G, you can't do that if it's actually something times G plus something times H. That's ruled out. So you have to balance the equation in order to solve the signature here. We check that the balancing equation happens, and that's it. It also has to be complete, and there's consensus level stuff too, like like the proof of work has to be valid. But this is all that's needed to check that the list of transactions doesn't actually create or destroy points. Yeah.
Is there any way you can kind of simplify it, like get rid of some of the older equations or older functions? And
Absolutely.
just keep like the previous state, but then keep your ledger kind of trimmed?
That's exactly one of the knock-on benefits here. So this is this exciting property, which is, and I don't even think I quite said it, but oh yeah, the second point here. So the validity is maintained in a very strong sense. So like being able to have correct signatures for all of the defects, and having all the defects satisfy the balancing equation, that proves validity of the transaction at any scale. So that includes the scale of all history. So if you view the cryptocurrency system as a mapping from all the Coinbases to the current set of unspent outputs as a single transaction, that works. That satisfies the same validity equation as all of the individual transactions individually. The validity of that contains as much information as the validity of all of the block level or transaction level verifications. So you can't balance all of history any easier than you can balance an individual transaction. Yeah.
Slightly random question. Are these transactions, like how much they look, like this is going to take up more space than the standard Bitcoin transaction? Like how much bigger than a standard Bitcoin transaction would this be? Or is this?
So I actually took a very high level look at this. I mean, there's two implementations of MimbleWimble that are currently deployed. Hey, there's probably a bunch of forks and stuff that people don't care about. Yeah, there's two main ones. There's Beam, which is a C++ implementation, and there's Grin, which is a Rust implementation. I guess I'm like showing my hand by saying what they did. Anyway, so
what version? Sorry, I was just kind of curious. What version of C++ is
that's a great question for you to look at.
Okay.
So I don't know what the details are. Like to actually turn these ideas into a production system requires a lot of additional work, obviously. But in principle, like what have we actually done here? So are commitments larger than values? Well, typically yes, right? Like how much space do you need to represent? How much space is used to represent a value in Bitcoin? It's not 32 bytes, whereas 32 bytes are required to represent a single commitment. You also don't have to give range proofs. So if you have unbinded transactions, when you give the amount, that's all you need. When you have binded transactions, you have to give these range proofs. And one of the interesting developments that's been ongoing over the past two or 3 years has been how do you make the smallest, easiest to verify range proofs? So unfortunately, I don't know what
It's roughly 500 bytes, I think, for bulletproof, approximately. What is your Grin? Yeah,
Grin is based on bulletproof.
and that's for one range proof. So you're going to have these commitments, which are like 32 bytes. So you have one for every commitment, so that's one for every input and output, and then you have these 500 byte range proofs for every one of those commitments.
You also have a signature for every transaction.
Right, which is also an elliptic curve point, so another 33 bytes for every one of those. It's significant overhead. But
So you could fit like a lot fewer transactions in a 1 megabyte block.
yes, yeah, exactly. But you get all of these really awesome properties.
Right.
Yes, so
Trade-off.
let's actually say more explicitly what the awesome properties are. So the properties that we've seen so far mostly are around obscuring the amounts of transactions, but in fact we also see that you can obscure the the transaction graphs. So in a given block, you just see inputs and outputs, and the way that I've described it's actually tractable to you could invest energy figuring out subsets of inputs and outputs, group together like balance for their given defect. But I think there are ways of mitigating this. But you get a huge privacy boost. Also, like it says here, when outputs are spent, their contribution of that output to the balancing equation has one contribution with the plus sign and one contribution with the minus sign, and they cancel. And so you can balance. So if your validity goal is you write down a balancing equation, you actually don't even need to know the terms that have canceled because they don't contribute to the net balancing of that equation. And actually, I think the next slide says something about this. Yeah. So, what do you need for the blockchain? You need the headers to make sure that it satisfies whatever consensus algorithm you had. You need all the Coinbase transactions. You need to see like when coins were introduced. You need to see all of the defects. So you need to see the transaction residues, those values. You need to see all the unspent outputs with their range proofs and some proof that they were ever included in some block. That's it. You can throw away everything else. And it's kind of interesting. So like, as a bootstrapping node, if your headers contain commitments to the current state, you actually only need the headers and this information, and you're just done. You can be perfectly justified in saying that you do not care about archival blockchain state. Like you get validity from a very small amount of information at the cost of not seeing old transaction. But at the cost of not seeing the evolution through time of the unspent output set. Yeah.
Just from an economic standpoint, since you're not seeing how much was your outputs, when you don't have access to that, you're just kind of proving that all the coins are equal, that the ledger is balanced. Does that also mean that if you were looking at like which transactions were the most profitable and which were kind of not the most profitable?
Well, I think if you're going to answer the question about, okay, so there's a few things going on here. So you've got the set of transactions, which tells a story about which pseudonymous individuals were paying with other pseudonymous individuals. That's already like somewhat gone. But even if you have that, understanding whether the transaction was profitable would require you knowing what was exchanged. And the blockchain does not tell you anything about what was exchanged. So you see a Bitcoin transaction, it could be a charitable donation, giving psychic yields, it could be payment for, something from the EMBO, I don't know.
Also, what about like volume? Like,
You don't get metrics. Like you don't get anything. That's the point. All you see is just random data, and through cryptographic magic, that random data, it's coherent. So your software client can tell you what your balance is, and everyone's private balances cohere together to create a ledger state which reflects, which has an invariant that no one can create money. And every time somebody's balance is increased, that increase came from deducting other balances. These are like the key conservation properties. So you get that, but you don't get to know how much anybody else has unless they'll tell you.
Gotcha. You can't see volume of movement or anything like that. It's all.
No, it's just. I mean, early on I had the Grin Explorer up, and it's actually I might put that up at the end again if the internet will cooperate. But all you just see is random numbers. It's very nice.
So one coin can have a different value compared to another, just with the transaction. So that means.
Well, what do you mean by that?
So okay, if two separate people are using it, and I guess the privacy is the value of the transaction. You can send one coin at two different values. Is that what you're saying?
I don't think so. I think that two different people can send the same amount of coin at two different values. Right? I'm making a very silly point about subjective value, right? Like, what's the Bitcoin worth to you, right? Like, how many hours would you exchange for Bitcoin? Like, you go around the room and everybody gives a different answer. I'm seeing something that's simple. So.
Because I was looking more at the speed of the transaction.
Oh yeah, again, this is like at a higher layer. So like, I'm just talking about the structure of the transaction. You can equip any blockchain mechanism or any consensus mechanism you want. So like, there's basically the two problems here. One of them is the accounting problem, and the other is like the agreement problem. So the accounting problem, I mean, you can do fun stuff like this and make it all secret, and then it's interesting. But typically, it's a pretty trivial problem. It's just you look at some numbers and like their sum should be equal. The problem of getting everybody to agree on what everybody's balances is, that's a very hard problem. And like right now, we have different approaches to this. So I can, we've got proof of work is the main one, but there's a lot of other competitors who are trying to take over.
I think proof of stake is like the one that's really seems like it's coming up. Just kind of from hearsay, not necessarily.
So if anybody's making odds on which is the best consensus algorithm, please say something. I don't think I would take a bet on that. Okay, so the last thing I want to talk about, if everyone still has energy, I'll talk a little bit about confidential assets. So this is this idea that you want to use the same sort of like commitment level trickery to have a single blockchain where you have multiple different kinds of assets, but you don't want any you don't want the blockchain to be doing explicit computation. You want it all to be very indirect and inscrutable. So basically, the problem here is like you have a bunch of outputs and you want to partition them into sets where they're mutually non-fungible. So like this output cannot be spent. These outputs cannot be merged together and spent as if they were the same kind of value. The idea here is that we're going to use commitments, but now we're going to change the group element that's used to hold the nonce. We're going to encode which asset we're spending in terms of that nonce. Okay, so So a really simple way to do this is to say you have now you have a new field on each output, which is just what is the asset type. So like you get some, you get some amount of space and you can describe your asset. Like you get, I don't know, 240 characters, and you can say what the foundational tweet of that asset was. And everybody has to tag the output with that. And then the consensus rules enforce that they can't be merged together and treated as fungible. So instead of tagging the outputs that way, we're going to tag them, but we're going to tag them in a way that's much more subtle. So for each asset type, let's generate a nums point. So again, a point where, as our like evolving software system moves through time, it's gaining more and more of these points, and we like pairwise don't know how to write one in terms of the other as a multiple. This is like a scarce and valuable resource. Like we want to sort of get all these points. And then we're going to associate each output with one of these points, but we're not going to do it just by writing what that point was. We're going to do something a little bit more clever. So now here, let's say that we have, instead of including commitments based on our fixed point that we had before, we're going to include commitments where the nonce is held by our special asset point. And the point here of this equation is that we don't actually need to have the nonce value held by that asset point, we can replace that asset point by a multiple of our other like fixed generator. We can let the asset point plus a multiple of the fixed generator, and we still get a commitment. So just to be perfectly clear, we can either think of a commitment as having parameters G and HA, where HA is the asset point, or we can think of it as having parameters G and this other point, HA plus R times G. Like, we can think of it in both ways, and we can transform one to the other at will, provided we know the opening information. So from the point of view of somebody who's like committing or opening the commitment, those are the same. Those are like the problem of opening that commitment is the same. I think I lost another slide here. Okay, so what's it? Yeah, and this is not supposed to be the end. Somehow I like lost the slide in the shuffle. But I can just explain in words how you can build a confidential asset scheme out of this. So the idea is that instead of the obligation being to balance the okay, so instead of balancing each transaction using a specific a fixed pair of a point G and a point H, now you're allowed to balance different portions of the transaction using these secondary points, and this will produce so each of the transactions will have a fee, and the condition is that the fee has to be a multiple of one of these points. And the main thing, okay, so without a visual aid, I think what I'm going to say is this is not going to make very much sense. But I'll tell you like the key thing, and like if you are sitting on the bus later and you're like thinking about it really hard, like you get it, but like at this point, like I'm going to just give up. But the point is that you're going to be able to sign for something using this weird point. So you're allowed. So now what we've done is we have transactions, and instead of having defects that are multiple of a particular point, we've now expanded the kinds of points that we know how to make into public keys. So we can take, and now instead of signing a transaction using an explicit key or using a defect, which it has to be a multiple of a given key, now when we get a defect, we can always sign it as if it were balanced using HA. So that's the main thing, is that we never, even though we're using weird commitments, and we're tagging the outputs with these weird commitments, so that an outside observer, they can't tell which of the assets the commitment refers to. Nevertheless, we can balance a transaction and we can make a signature at the end of the day. So I apologize for somehow I lost the slide. It happens. But yeah, it's entropy. It always sneaks up on me there. But yeah, so I guess what I'll say is it's I think that there's enough. If you take a while and you digest the stuff that we've been talking about, and you think about, okay, so I have a bunch of outputs which are tagged with points like this for various A, and now I write the sums of the input commitments minus the output commitments. The output commitments minus the input commitments. Now I want to create a signature over this. If you write down that equation, what you'll notice is that you can actually write it as in terms of points like this for whom you know how to make signatures. So that's the point. Okay, so I think I've taken up enough of your time. That's the end of the talk. Happy to take more questions. I mean, how many of you have played around with either Beam or Grin?
Did you guys run the wallet for Beam or no?
I haven't tried Beam. I messed around with Grin, and it's sort of interesting. Like so Grin uses a slightly different mechanism than the mechanism I described for constructing transactions. So it actually has a 3-part transaction construction mechanism. So like, let's say I want to pay one of you. So I start out and create a transaction template of some form. Then I have to send you a file, and then you add some of your information in that file. You add a partial signature to that file, and send it back to me, and then I complete it using my own signature, and then I can broadcast it to the network. So it has this like really interesting, weird, like 3-way interactive transaction creation mechanism, which if you're used to something like Bitcoin is like, or really like anything, it's really weird. And I think that one of the interesting things that people are working on is like, how do you reduce the amount of interaction in creating transactions for these MimbleWimble based protocols? And it'd be really cool if that catches on.
Yeah, so I feel like the developers have to be trusted very closely in order for MimbleWimble to work due to the non-transparent transactions. You could have something like a pre-mine or a Genesis block that's going specifically to the developers, Satoshi coins, right? Those are like very transparent. We can see when they move around. But in the case of Beam and Grin, we have to trust the pseudonymous developers.
I think you just trust the cryptography. I guess it kind of
Coinbases are open. Coinbases are public.
Oh yeah,
so that's one critical.
Yeah, so if you're worried about, so I didn't discuss this at all. So like you have, at some point coins have to come into existence.
Sure.
So one way to do this is you could say, what that would be very simple, is you create like a Genesis output and you publish you publish the amount and a proof that it actually. I'm not sure how you would open that commitment without revealing. Actually, if you spent it first, then you could later open it, proving how much was in it.
Sure.
Yeah.
Is that something that developers do?
No. I'm just sort of speculating about methodology. The way that it works in Grin, and I think probably Beam as well, is that the Coinbase transactions are in the clear, so they have a commitment to 0.
So the like inflation rate is known upfront and it's verifiable in the protocol.
But as soon as you have, if you have Coinbase transactions in the clear, then what you might be worried about is some sort of flaw in the cryptography, which allows people to
Unverified transactions.
Yeah. And this, as far as I know, I haven't seen people raise that particular complaint against this method. So if you have Coinbase transactions in the clear and MimbleWimble style confidential transactions, I think, as far as I know, this is sound. Like it actually does, under reasonable assumptions, enforce ledger balancing.
So with one thing, and I wasn't sure if I got this right. So with Grin, you have to have both clients like online in order to.
Well, they don't have to be online, so you do have to do 2 rounds. So like you can be offline, that's fine, and I'm going to email you some like weird JSON document with a bunch of random stuff in it, and then whenever you're ready, you can go online, do your signature thing, send it back to me. I do my thing, but it can be like very asynchronous.
Okay.
It's not like you can contrast this with Lightning, where really there's a whole handshake, and like at the end of that handshake, the transaction goes through. So like you have a bunch of different hops, and everybody has to sort of be online all at once, or else it times out.
Yeah.
Grid is like this in the sense that like you are waiting, you're blocked by the non-responsiveness of your counterpart.
Okay.
So, sorry.
Yeah.
So for both Grin and Beam, can you actually run like one of the clients on the server, which is on 24/7, and it just kind of waits for other clients, like you're doing a
Yeah.
shop or something?
I mean, yeah, certainly. You can, so are you asking whether or not, okay, so are you saying, I have an e-commerce site, I want to accept Grin, I'm going to expose my Grin wallet to the internet and people can pay me using the wallet-to-wallet connectivity? I mean, you can do this. I don't know, I mean, I don't think I would at this point, just because I don't think the wallet, that's part of the design. Like, the wallet is not designed to be exposed to the wallet API is not designed to be exposed to the open internet. And I don't know if anybody who's made like a safe Grin tool for web integrations, but certainly in principle you could do that.
So the whole thing would be that in this case, you would have to make the wallet be actually actor safe and kind of guard safe or actor safe, but still implement the same MimbleWimble protocols.
I mean, this is a general problem, right? Like you have some piece of software, and you have to assess whether or not, like, do you really trust? Like, do you trust exposing it to the open, to some, to the open? Like, if you do, good for you. If you don't, you build some sort of service that mediates its interaction with the internet, possibly adding additional authentication, blah 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 blah. But it's just software.
Right.
Do you have a question?
Yeah, like to answer that, like, so how would the user interface look for mass adoption?
That's a great question. I mean, I think that this is something that's like, this is a question that applies to like across the entire cryptocurrency space. Like we're very used to having you want to pay for something or you want to participate in a service, and like the steps that you might go through are, either you get direct access to the service, you have some guest account, whatever, you do your thing, or you register an account and you have a username and a password. Like there are all these like familiar flows. With cryptocurrency-based things, you want to use something and then you find out, oh, I need additional software, or I have to just use this as a custodial solution. Like I have a bank account at Coinbase or something like that. And like you could certainly have like potentially in the future. It doesn't matter if it's MimbleWimble based coins, if it's anything. You could always have the option of a custodial account at your account at Coinbase. It doesn't matter what crypto it is. Like they're going to tell you what your balance is, and like maybe not. But if you're going to take the next step and you're actually going to verify your balance for yourself, that definitely requires additional software on top of the web application you're visiting, which is a really weird experience, and I think it like very much appeals to some people. And I don't know like whether it's a generational thing where like people who are 12 today will grow up thinking it's like totally normal to like have your like subsystem of computing which controls like your money, your self-sovereign, or whether it will completely fail. I mean, I think it won't, but like it's hard to predict what the behavior of people who are coming of age today will be and what their assumptions will be. I don't know, does that?
Yeah.
It's sort of a hard question.
Yeah.
It's kind of on this idea of what you were talking about, this e-commerce kind of direction, like why would you have this open up? But if you're the only one that cares about the value that is being exchanged, and that value is only to you, then you can see a purpose for that, maybe.
Yeah.
Right?
Well, like,
why would you use the privacy for e-commerce?
I think the idea is that e-commerce has value outside of that network. What I'm more thinking about is Overstock didn't know what the value of Bitcoin was early on, but they had an assumption that it was going up or down. But they still knew that the asset had value regardless. So I'm thinking kind of, it turned out they were kind of right if they were early, but what if it just went down to zero? I mean, it mattered to the CEO because being in that space at the right moment to be in that space.
So before we continue, I just want to like give if there's anybody who's like sort of ready to get up, get a beer, some food, make a donation, or just leave, like whatever, like please don't feel like you have to just like sit here. We're going to continue to have the discussion, but like I just don't want people to like rest on the floor. But it's a very interesting question. Like you have a lot of different options for using cryptocurrency technologies now, and I think that, like it works. My personal view is that it works best if people base their decision making about this on their own needs. And so, like for a lot of people who live in the United States, I think that it's most interesting as like a toy or a hobby. I mean, this is just like the world that we live in. For people who are abroad, it may allow like capital exfiltration that wasn't possible before. For people who are in like sensitive areas, like maybe you're an investigative journalist and you need to pay your sources. Like, there's all sorts of like great ways to use privacy coin. For people who are just buying stuff online, like it's sort of hard to imagine that you would get to the point where you're about to pay for some online thing using a privacy coin where you don't already have information about your name, address, phone number on record.
It could easily be like, you could link it back, which is the reason why we don't say that.
And the amount too, right? Like the amount is in the database regardless of whether or not it's on the chain. However, even if that's the case, with something like Bitcoin or I mean, I think a really good counterpoint is the way that people typically use Ethereum is to have a single account and use that account for everything. So this is a model where you have essentially a complete record of all of your transactions in a very easy format about which there's no ambiguity over the entity associated with the account. With Bitcoin, there's some ambiguity, not a ton, but you still have this public database of transactions, and if it ever becomes known that some group of outputs is controlled by you, now suddenly there's a lot of information about your private finances that's linked. Whereas with the privacy coin, even if you're transacting on a public website, in order for that to become public information, there would need to be a database or something, right? It's sort of like using a privacy coin with a public website is kind of like using a credit card with a public website in the sense that it has similar privacy guarantees. People still know who's doing what, but that information is held in it's not public information broadcast. And it's not, I understand, even in Bitcoin and Ethereum, it's not 100% public information, but it's way closer. I don't know if that's
So in that theory, would a MimbleWimble like Tumblr be beneficial?
Well, that's the thing. So in that situation, you don't actually whether or not you're using a Tumblr is relevant because you've already leaked that certain outputs are associated with you. You've already you're doing you're citizen of the world doing commerce, whatever, and all the companies that you interact know the transactions that you had with those companies. No amount of Tumblr is going to change it. That's an inferior to unless we have some way of, unless we decide to go full trustless and have a system where you can transact anonymously with people using some drop games or some fancy stuff like this to get your whatever you paid for, that's going to be the state of the world. The organizations know a lot about each other and you. And in particular, they know a lot about your own personal dealings, regardless of what the organization is. Yeah.
So if you use this protocol basically on all your transactions, you can basically kind of protect yourself from taxation.
No comment.
So, this is another, mentioned that you were using JSON to exchange the data. Could you actually use
Can
any
you
sort
explain
of?
what I think there? You said something.
So this is the technical question about the format of Grin transactions. And you know what? I recommend that you download Grin and you go to the test network and you construct a transaction and you accept it.
No, I just was wondering if you could actually change it from being like a binary or a protocol, type of protocol, rather than just solely a
I mean,
JSON.
I'm going to give you the same answer. Like, this is a thing that involves the details of the implementation, and you should play with the software.
Okay, thank you.
Yeah. All the, like,
You gotta change some numbers back and forth.
yeah.
Somehow, somewhere.
Like, unfortunately, like, you know, if you're designing software and you have to decide how to marshal data across a communication channel, like, okay, you made a decision, and now everyone else has to go look at what your decision was in order to find it out. It's like, it's not like everyone is, like, wouldn't it be weird if we lived in a world where everyone agreed to use exactly the same wire protocol all the time? Like, wouldn't that be terrible?
This is more about the team that found this. They came out of Israel, and I'm wondering how much.
Which team are you talking about?
The brand. So I just read like this whole medium on the. How much do you think like Zcash and other coins are kind of influencing the roadmap of this?
I mean, I don't know, honestly.
Because it has like so many similarities.
Well, I think that having a more private ledger is a worthy goal that is pretty much like universally held as a worthy goal. I mean, I think even at the beginning, like Satoshi, you know, in the Bitcoin white paper, speculated about like the likely privacy benefits of the system. Like that has been a concern since the very beginning. We now know that Bitcoin security is very imperfect. Privacy is very imperfect. I mean, security is imperfect too, but I think we have a slightly better understanding of it. But you know, with comparing MimbleWimble to Zcash, I mean, there's so many dimensions there. So like, if you had a system, so like Zcash and these systems based on zero knowledge proving. So with a system like this, you can completely hide the transaction graph. Like you can get not quite information theoretic guarantees, but something close to that for whether or not someone can link two transactions. So you know, I think there's kind of like a moral hazard there. So you have the ability to essentially create transactions. So you can create a proof that you have a claim on some value that's redeemable later without revealing information about how the claim was constructed. Right? Now, this sounds really great, but what happens if you choose a value that's never been observed on the chain before? You commit to that, you put that value into this scheme, and then later redeem it. So now there's exactly two transactions of that value. And one of them places it into this very private pool, and the other one redeems it from that pool. You know, or like maybe it's offset by exactly the amount of the median fee at that time. Right? Like you have that.
That can also be time.
What's that?
It can also be time instead of that value being the difference.
Oh well, all I'm saying is that like even if you have excellent primitives, like there's some systems level design stuff. So it's like with something like MimbleWimble, you know, you still have groupings. Like if you're watching the evolution of the blockchain, you still know, like at least per block, or if you're watching the gossip network, you know per transaction like which outputs are linked to which inputs. So you have like a fuzzy transaction graph that you can see. Whereas with Zcash, like there's no fuzzy transaction graph to observe. But if the values are public, there might as well. You know, if people are disciplined and like you only transact in like multiples of 10 or something like this. You can do that. And so I would just say like this. I'm giving an example to illustrate that like privacy is very complex, and you can have systems with like relatively weaker privacy achieving a better outcome for their users than systems with a higher privacy, even if those systems could have much higher privacy if they were designed in such a way that they couldn't be used. Like, how do you prevent users from leaking information? This is actually what we were talking about a little while ago. It's like, you're leaking information whenever you're telling anybody what transactions. If I do a transaction with somebody, like, that's one more person who knows about my transaction graph. Something about my transaction graph. So there's like there's a trade-off there. So I think it's interesting though, like, what's that?
It all depends on the environment, and I get what you're saying.
Yeah.
There's certain environments in the world where privacy is much more important.
Well, there's ways of there's lots of ways to leak your private information. And, like, it's maybe someday we'll have like the best privacy coin. I don't even know. Like, that's
Tor would be a good parallel to that, like the exit nodes that are controlled by AAA agencies. So cross correlating to like certain users accessing certain sites. So,
yeah.
The more exit nodes that you control on Tor, the more you can see the traffic of a certain user. So
how would MimbleWimble compare against, say, Narrow and Enigma?
So I don't actually know anything about Enigma. I kind of thought Enigma was a different scope. Yeah, but I don't know if it's like a value transfer.
And then others reinvent themselves, so.
Oh, okay. Yeah.
I don't think anybody's.
But Monero, so Monero has a sort of a different model. And again, I mean, it's like you have Zcash, you have Monero, you have MimbleWimble, and they're all aiming at the same thing, and they're making advances in kind of like different sectors. So with Monero, what you're doing there is you're obscuring the transaction graph by adding decoy inputs and by obscuring the amounts of transactions. So this confidential transaction thing with range proofs and blinding factors, that's live on Monero right now. It's been live for a long time. And the privacy benefit there is also that you can't not blind your output amounts. So it's private by default. But the defect to this is that, and it's kind of like a universal defect. Like there's this methodology by which, like, okay, you're running. So let's say that you are financing the operations of like a distant group in some country somewhere. And in order to, so we don't live in a world where you can just pay everybody with Monero all the time. So you need access to some exchange where you can convert that. Maybe you can even convert it to Bitcoin. You might convert it to dollars or your local currency, whatever. Or you might convert it to your local currency as a face-to-face thing. Although that seems sort of difficult at scale to keep that secret. But nevertheless, like you have these incoming transactions, and then you have to do some interaction with it. A member of a very small set of service providers. And as soon as you're in between a transaction source and a transaction sink, it's possible to link the person redeeming the value at the transaction sink with the person receiving the value at the transaction source.
Are you saying that in Monero?
So there's like theoretical attacks on Monero, which are like these active attacks. But like, the thing is, like, this isn't. It's not like, oh, Monero is broken. It's like, no, like as a population of people resisting interference, like we just don't know. We just don't have operations security. Like you can't take privacy coins in and spend privacy coins out. You have to spend privacy coins to buy something else, and there's very tight controls over. If you want to do this at some scale, there's very tight controls over who can convert your privacy coins into something which general service providers will need. And like you're now between two points which can both be compromised. Yeah. So, I mean, in some sense, it's like, privacy coins are fun, but like operational security is a real concern, and adoption is a real concern. We'll be able to get privacy. I used to think we would need privacy before we get adoption, but I think it's there. All right, should we turn off?
Yep, you want to say goodbye to YouTube?
I need a beer. I'm getting a little hoarse.
All right. And you're done.
All right.